All right, so let's talk about data definition. As we'll learn a little bit later, we'll see that there's two specific types of commands that we'll be using. A set of commands will be for us to be able to create the data, right, or create the structure of the data, right? And there's going to be another set of commands that is going to allow us to interact with that structure, right, of storing data, following that schema, or retrieve the data, or update the data, or delete the data, right? So there's two separate set of commands that allow us to do that. So let's take a look at first at the data definition. How do we define it? How do we define the structure of the data? So as we said earlier, the basic structure of the data in a relational database is the table, right? It's kind of our bucket, you know, of where our data set, our data points are going to live, right? So a table is a collection of data points, and these data points we're going to refer to as records, right? And then physically is how we think about it conceptually, right? They make up the rows of a table, right? But conceptually, we refer to them as records, right? And each row in the table has multiple columns, and each column is typically of the same data type, right? So one column might have the date of birth, right? And its data type might be date. You know, one of them might be how many seats are left in a particular section. So that might be an integer, and they're all the same type. We call the structure on what are the fields and what their data types are and the names of these tables. We refer to it collectively. We refer to it as the schema. Right? So the schema is what defines a particular table. So this table, the schema of this table is that it has an enrollment. It's called enrollment. It has a primary key called EID or enrollment ID, and it has the following fields: section ID, student ID, and the grade. So that's the schema of that particular table. And these tables might have several records that will establish relationship between the various records. So, for instance, here we have the student table having a student ID that uniquely identifies the student, and it has been declared as a primary key because it participates on relationships with other records stored in other tables. For instance, the enrollment table has a field called student ID that has values that are meant to be interpreted as referring to values in some other table, right? So we refer to as the fields that hold those those unique identifiers. We call them the primary key, and it's primary key because it's participating in a relationship. And indeed, this field we refer to as a foreign key, right? It has values that refer to values referred elsewhere. These could have been just integers, right? They could have just been integers. We didn't have to declare them as primary keys or foreign keys. But then then we would not. We could have, for instance, type values here. 33, for instance, and there's no student number 33, right? Just by declaring it as an integer is not enough of a constraint, right, to establish a relationship between this record and that other record. By saying that this is a this is a foreign key, now I'm telling the database that said, hey, this is not just any integer. Okay, this integer has to refer to some record that already exists. Okay, so I can only type here 11 or 22 because those are the only primary keys that are over there. Make sense? Okay. Also, by making that a primary key over there, I'm telling the database, hey, these are not just any integers, right? These are integers that somebody is pointing to us. Okay. So if somebody is indeed pointing to us, for instance, I cannot remove the record. If I try to remove the record, right, and somebody is pointing to me, the database is going to stop me. It says, no, we can't do that. Right? If I let you do that, then I would be in an inconsistent state. Right? I would have this record over here as an orphan. Right? It would be pointing to somebody who doesn't exist. There's no parent. Yes? So by establishing these constraints, right? We are asking the database to enforce certain certain rules that maintain what is called referential integrity, right? That this is a reference, okay, meaning I can only put an integer here that has a valid value of some record that actually exists. Okay, so I cannot put just any number there. Okay, that maintaining that is called referential integrity. Okay, other things here. Let's see. We have the enrollment has two foreign keys, right? Pointing to the student over there and pointing to the section. Right. We might, for instance, say that the combination of student ID and section ID might be unique, right? Because a student cannot be enrolled twice in the same section, right? And that's perfect, right? We could, for instance, decide that the combination of this key, this unique key, plus the student ID, plus the section, that whole thing needs to be unique. Well, at least a combination of student and section. Meaning that I'm asking now the database, hey database, make sure that the combination of these two values, these two fields, is unique, right? Because I am enforcing some rule, some business rule. Somebody at the registrar said a student cannot be enrolled more than once in a section, right? And so somebody's question, how am I going to enforce that in the database? Right? You have to enforce it, right? So that rule drives your selection of primary keys and foreign keys, and what are you going to decide on what the schema is, right? So your schema should fall right from the requirements or some narrative that is given to you. In this case, is a university database. Make sense? Right. So a schema always follows some business rules, and you're looking to enforce things. The most obvious enforcement is that this might be an integer, that might be a character or a string. Those are obvious. Right? The more nuanced ones are how do you enforce relationships. That's are much complicated. Normalizing data. So notice here we have a table called the one big table, right? Where we might have information about. Let's see. We have student information here, right? We have student names and graduation year. We have some department names over here, right? We have chemistry. We have some title of some courses, who's teaching it, the year that it was offered, and the grade for that student. Okay, but notice that all these folks. Joe and Alice and Bob and Dan looks like they are all enrolled in a course in the calculus course in the chemistry. Wait, what?
Department name. So they're taking calculus
in the chemistry department. I think that should be math or thermodynamics. I think this should be backwards, opposite. See. Anyway, so notice that there's really no need to repeat this over and over and over, right? To capture this information, right? It would have been better to perhaps capture the information about this calculus and the department name in one single place, right? So if indeed somebody moves, we're expecting all to take this together, and somebody just moves around, and we update just one of them. Then we would be inconsistent. So what we try to do is that instead we try to break this up into multiple tables, right? And breaking up into multiple tables is referred to as normalizing the data. We normalize the data. We break it up into smaller chunks. Okay, we didn't. All right, we'll talk about that normalization. There's a whole presentation on that. Null values. What null values mean is that we don't have value, right? It doesn't mean that null is a value, right? It means that we don't know what the value is, right? And since we don't know what the value is, there's nothing we can tell you about it. We can't tell you if it's bigger, if it's less than, if it's equal to. We don't know, right? So So fields that have null values don't participate in queries, right? So you might do a query, and you might be asking yourself, well, I was expecting more records to come back. Why are there more records? And the fact might be that a lot of the fields that you're using to do your query might not have value, right? Might have null values and do not participate. I don't know if it's bigger. I don't know if it's smaller. I don't know if it's equal. It's null. I don't know, right? And it means that, as if somebody's filling a form and it doesn't actually provide a value for that form. You don't know. It's not blank. It's not 0. Okay, it's not some flag. It's just I don't know. So just be careful with null values. Keys are used to be able to uniquely identify records. It's very important, even though databases don't enforce this. Databases by default don't enforce that a record needs to be unique. Okay, when you're programming in Java, C#, when you instantiate an object, right, it is by default, right, by its nature, the fact that it's occupying some memory space, right, some bytes in some RAM, gives it an implicit identity, right? An implicit uniqueness. Okay, you cannot have two objects occupying the same memory space, right? Even if they have the same values, right? You might have exactly the same first name, last name, whatever, right? Phone and whatnot. Even if they have the same state, they have different identity. Okay. Whereas in a record, right, in a database, having the same exact values implies that you're the same thing. I'm going to treat you identical, right? So there's no way to implicitly create identity or uniqueness. So that's why we need keys. Keys is a mechanism that allows us to uniquely identify a record. If you have two records and they have the same exact value, there's no way for the database to distinguish one from the other. Okay, as opposed to in Java, right? If you have two instances that have exactly the same value, they're still assigned to two different variables. Yes. Yeah. So we can't use by in general. Obviously, they are occupying a different space when you store them in the file system. Yes. But we typically do not use that as a way to identify a uniqueness, right? Or like in Oracle, sometimes you could use the row. What row is that record actually occupying? Typically, we don't use that either to identify a uniqueness about a particular record, right? Typically, the databases cannot guarantee the order in which the data is stored, right? Order is only useful for human beings, right? That we like to see certain things sorted in a particular way, right? For a database, it's order is meaningless, right? We might have indices that might order the database in a particular way only for optimization purposes, right? But in general, we don't sort the order. We don't sort anything in a particular order, right? We might say, well, what if you have a phone book, right? Won't you want to sort it maybe by last name? And that's true. That's if you want to search it by last name. Then you want to sort it by last name. What if you want to search it by phone? Well, then the sorting by last name is useless to you, right? So the ordering really matters by how do you want to consume the data, right? If I want to consume it, if I have the last name, yes, I wish it would sort it by last name. Oh, actually, all phone books are sorted by last name. But if you have a phone number, then that sorting is useless to you, right? You still have to use linear search to search it. You would wish that it would sort it by phone number, right? And that's what indices do. An index, when you create an index, right? You index it by a particular field or multiple fields, right? Because you want to consume the data by that field, right? Because you normally search it by last name or you normally search it by phone numbers, right? So you have two indices, an index on the phone number and an index on the last name. and one of them will be sorted by the phones, and one of them will be sorted by last name, right? And that's what keys allows us to do. Typically, you allow us to keys also allow us to group keys together or fields together to make them more unique. Okay, perhaps maybe my first name is not unique enough to make me unique in this university. Maybe it's unique enough in this class. I don't know, anybody else call Jose here? Maybe Jose is just enough to make me unique in this classroom. I don't know if it's enough to make me unique in this building. Certainly is not enough to make me unique in the university, right? So I combine my first name and last name, perhaps is enough to make me unique in the context of this university, but probably doesn't make me unique well, maybe I am the only Jose Anunciado in Boston, but certainly not in the country, right? So depending on the context, right, you might need to make combinations of keys or fields to make you more unique in whatever context you choose. Yes. But there's certain fields that if I keep adding more and more fields, don't make you any more unique. Okay. So we say that adding more keys to an already unique combination, right? Those keys that don't make you any more unique, we call them superfluous. Those keys are unnecessary. You don't need to. I don't need, for instance, in this context, I don't need my last name, right, to make me more unique. Just my first name is enough. So my last name would be superfluous, okay, to make me unique here. Make sense? Right. Selecting keys. Typically, you want to choose something that you know is going to be unique. Maybe an email. Ideally, it would be something that maps to the physical world, right? Like an email, right? It says, okay, so this is something that maps to a physical or something that I can actually. But most of the time, but oftentimes, they are not as convenient to be unique, right? To be as unique, right? And oftentimes we are forced to use an arbitrary unique key, right? And that's where things such as credit card numbers and social security numbers and student IDs and all those are arbitrary, right? They're artificial keys, right? That don't map to anything physical, right? And perhaps we might say that our identity is just a collection of arbitrary keys, right? That's our identities of all my credit cards and all my social security. That's what makes my identity. And within their context, they're meant to be unique, right? So if I have a phone number within the context of the United States, that makes me unique in the United States, right? But probably somewhere else in some other country, they might have exactly the same phone number, so I need to add a country code, right? And that makes me unique in this planet. And when Elon Musk gets us to Mars, maybe somebody else might have a phone number that's exactly the same as mine here on Earth. We'll have to add a planetary area code, right? That makes it unique in this solar system, and then so forth and so forth, right? Let's see. Typically, we don't want to choose uniqueness based on the data. Okay, we might look at the data, like for instance here in this room, and we might say, oh, everybody has a different last name. Well, I don't know if that's true, but everybody has a different last name. Oh, let's use the last name as a primary key, right? And so that's a flawed strategy, because you cannot guarantee that particular field will be unique going forward, right? If you increase the scope of just this room and you go to the university, then that strategy might not work, right? So it should never be based on the content. If you look at it and says, oh, all these values look like they're unique, let's use that field, right? Instead, it should be the intent. What is it? It's the last name? No, that's not a good idea to use last names, right? Is it the email? Maybe that's a better idea. It's an email, right? Domains are unique. There's a domain somebody maintains a uniqueness in domain names. So maybe that's a better idea. So always use the intent of the field to decide on whether certain fields are a good idea or not. And combining fields can be used to enforce certain restrictions, certain constraints, such as not allowing students to enroll more than once in a particular section, so that the combination is unique, right? You might have student repeated multiple times in the table, but the combination of student and section now is unique, right? So we'll talk about that compound keys a little later. Other types of constraints. So, for instance, here in the domain in the project description, in the narrative, as we interview our clients as they describe the problem to us, right? They might describe things such as, a professor can only teach one section of a particular course. Okay, that's a business rule, right? Or a professor might teach that course only once a year. I don't know, whatever arbitrary rule they might come up with, right? We need to enforce those rules, right? And so we might decide certain combinations. So, for instance, here says that if we combine the course ID with the professor with the year offered, it says that professor teaches at most one section of a given course per year. That might have been a requirement, right? We need to enforce it. Here's another one: course ID and year offered. A course can have at most one section per year. Might have been a business rule, right? We need to enforce it. A professor teaches at most one section a year. So here's an example of some of these constraints and where they might be flawed. So here's one where you have no constraints. That you have professors 1, 2, 3 and 2, 3, 4 teaching whatever course, whatever year. But if you look at each one of the constraints, you notice that the first two violate the first constraint, right? That we had the same professor teaching twice, right, in the same year. This one, the course was being taught twice in the same year. Here, the combination that a professor in a course in a year was offered the same twice in the same year violates the third rule, right? So depending on what rules you have, drives what constraints you're going to add into your database. Duplicate records. Most databases don't enforce the fact that records need to be unique, and so you're going to have to do that. You're going to have to provide one of the fields to be unique, either with unique or primary key, to make sure that if you do insert two records that are identical, that have the same values for all the fields, the database won't be able to tell them apart, right? So if you say, delete a record where so-and-so field is equal to whatever, and both records have the same exact, meet that same predicate criteria, both records will be removed. Even though you might have intended only one of them to be removed, okay? But the database, there's no way for the database to distinguish one from the other. So be careful. Primary keys. Again, primary keys are constraints that allow you to enforce certain rules for when records are going to participate in a relationship, right? So primary keys allow you other records to refer to you, right? So that if you try to remove that record, it'll stop you. The database will stop you and say no, because you're violating a referential integrity. IDs are usually IDs are chosen as primary keys, and oftentimes we just let the database generate them, right? And just because it's an artificial key, that ideally we could have had a natural key as opposed to an artificial key. A natural key is one that maps to something physical, like my first name, my last name, which at some point probably 200,000 years back, first name and last name was also very arbitrary. Some grunt that somebody came up with, to identify me from someone else. Probably that was very arbitrary back then. Why one grunt versus another grunt? or some other rules that were very arbitrary at some point. Leonardo da Vinci, from a particular town. That's arbitrary, right? I'm going to use the town you came from as a uniqueness of where you are, or your parents, or your male parents, whatever they were called. You inherited that last name going through generation. That was arbitrary, right? So all these ways that we've been, capturing ways of uniquely identifying ourselves, have been at some point arbitrary, but have made it into society, into our culture, and now we refer to them as natural, right? As natural, and certainly being questioned or challenged in our new age. Yes. Foreign keys are the mirror image of primary keys, right? Those are values that refer to primary keys to establish a relationship. So some of these are foreign keys from our previous examples. You have major IDs and department IDs, course IDs, student IDs. In these tables, right, are referring to other records that have declared them as primary keys, right, to establish a relationship between the records. So throughout the semester, we're going to be using the following nomenclature to identify what fields mean if you see in a quiz or an exam or an assignment. The first one will be the name of the table. Primary keys will be underscored, right, bold, right, and italic, right. If it's a foreign key, it will be bold and italic, but not underscored, right. So this is a foreign key, right. It's referring to something outside. Fields that are not bolded or italic or underscored, they're just normal fields, right? They're just data fields, right?
That's unique to just that record.
Unique. Yes, but it's just holding data. It's just holding data. So typically, all the fields all these other fields, this is really the data that we want to store. That is the actual data that we want to store. Everything else, all these other fields, right? These are fields that establish relationships between records, right? Establish the structure of the data, okay? They don't actually hold any data, right? They're not part of the data that we want to store. They just hold the relationship between the data, okay? So this is data fields, right? Where these are all relationship fields, okay? When we get to UML, in Unified Modeling Language, we only care about data fields, right? We don't care about their structure fields, right? Instead, we use graphs, right? A class is a box, okay? Foreign keys and primary keys are lines between the boxes, right? And so we graphically represent the same information, but graphically, right? So that leaves us to capture only the data fields. Keys are as they're foreign keys. So, for instance, you have a student referring to a department and how they now in relational databases, these keys allow us to navigate from one record to the other record. Right? We say, well, we have a particular enrollment and we have the value of the student ID. It allows us to identify that particular record in some other table, the student. And once I'm at the student and I have a major ID, that allows me to navigate to a particular department. Okay, make sense? This allows you to navigate both ways, right? I can say, for a particular student, give me all the departments. For a particular department, give me all the students. Right? It allows me to go about both ways, as opposed to in Java. Java, typically, the relationships are one way. Right? If you have an object that has an instance of another object, right? I can navigate from that parent object to the child object. Typically, the child object won't have a reference back to the parent object. Typically, we could, but typically it isn't. Right? Typically, you navigate from parent objects that might have an instance or maybe a collection of instances, an array of other object instances, right? and you can iterate over those children. But typically from there, they won't have back a reference back to the parent, right? So that's quite different on how we do data modeling in both in these two different worlds, in the object world and in the relational world. And we'll talk about some what the challenges of going from one to the other, right? Oftentimes we say that there's an impedance problem, right? There's a gap. There's a very difficult gap to fill between these two worlds, right? And ORMs will allow us to do that easily. I thought we did that. All right, referential integrity, as I mentioned earlier, enforces the fact that if you do have a relationship between two records, that you can't just willy-nilly remove one without removing the other, right? Just like if you have a directory and you have files in that directory, typically the file system will stop you from removing the directory if there's still files in there, right? So similar here. If you have a parent department and you have a whole bunch of students enroll in that department, you can't just blow away the department, right? And you can leave all the students, just hanging there, pointing to a department that doesn't exist anymore, right? So referential integrity enforces these kinds of disallowing these violations of these relationships. So for instance, you have these students, Amy and Sue, that are enrolled in the math department. And what do? I just remove the math department? What happens to these references? Right. So typically, we want to tell the database what to do, right? When these integrities are going to be violated. What do you want to do? One of the things is to cascade delete, meaning cascade the action that you did with the parent, cascade it also to the children, right? Would it make sense here? Maybe not. If I remove the department, do I also remove the students? That makes no sense, right? That if I remove the parent department, I somehow lose references to all my students in that department. That makes no sense, right? The other might be that if I do remove the department, the other thing that I might configure the database to do is to just make these null, so that they are, I don't know where they're enrolled, right? I don't know what their enrollment is. Or I might say that if I remove this, perhaps I change the value to something else. Maybe all the computer engineers are now enrolled in computer science, right? They're just changed college. Okay. So cascade allows you to cascade these things, right? Sometimes the cascade does make sense, right? Say I have courses and I have a whole bunch of sections that are referring to the course. These are the sections for a particular course. If I remove the course, the section should be removed as well. That makes sense, right? To cascade the delete on the course, to cascade it on the sections. That makes sense, right? But if I remove the department to cascade that onto the students, that makes no sense, right? So you have to choose, right, which ones make sense or not. Yes, you can do an update, you can do a change, right? Set it to a particular value and cascade the different references back and forth. And you can either change it to set it to null, referential integrity or key constraints. So these are in general are referred to as constraints, right? The most simple constraints are data type constraints, right? This has to be an integer. This has to be a date. This has to be a Boolean. This has to be a varchar, right? Those are obvious, right? But then there are the more nuanced constraints, right? That this has to be unique, right? This is participating in a relationship, okay? If you remove this, you also have to remove that, right? So those are more nuanced, integrity constraints and whatnot. All right, so to establish to create these tables in SQL, we use the create table command. You type create table and then the name of the table that you want to create, and then the fields that you want to the schema of that table. Right. So here's an example of creating the student table that has a student ID. The student name that's 10 characters long, Notice the constraint not null, so I need to have that. That's kind of like in a form. It's a required field, right? Meaning I won't accept this form unless you give me the value for that field. That's what the constraint means, right? I have to have a student ID. I have to have the student name. Everything else is optional. I don't care if you tell me the major or the graduation year, right? That you can leave null, right? And that student ID, I'm adding the constraint that, hey, that's a primary key, right? Meaning other records, I'm going to refer to that field, okay? And the major ID is a foreign key. It's referring to some other records. So other records are referring to me, and I am referring to other records. Right? So I am somewhere in the middle of a relationship, right? So I'm declaring a major ID as a foreign key that references a department. So presumably, department has a primary key, presumably. And I'm establishing some updates meaning that if this major ID is updated, meaning if the major changes from 20 to 30, right, I want to cascade it, meaning I want to change. If my department changes from 30 to 20, I also want to change from 30 to 20, okay? And if my department is removed, I want to be set to null, meaning I don't know, I'm an undeclared student. I don't know where I'm going. Plus, I can add all sorts of checks to validate, make sure that the student ID is greater than 0, that the graduation year is not, it's not before the school was established. We can put all sorts of predicates to validate. Yes?
So the cascade is written in the children, right? Because this student is a child of the partner.
Yep. Right. Yes, in the child.
The cascade is for itself. What
Yep.
happens if parent changes, right?
Yeah, meaning I have a key. So this the parent. So there's a foreign key to my parent. If my parent changes, I want to change.
Okay.
Yeah. Yeah. Also, we'll see. Also, notice that the direction is different, right?
The reference is some departments pointing at me, right? It says.
Oh no. I am pointing to the department.
Okay.
Right. So notice major ID is declared here. Yep. I have a value, and I'm saying that value here is referencing the primary key in the department. So the department has a primary key, and I'm saying that my major ID, the values here cannot be anything other than whatever primary keys are there.
Okay.
So if my primary keys are 10, 20, 30, this value can only be 10, 20, or 30. Okay. Right? It can't be 1, can't be 2, can't be anything other than those 3 values. Okay? But I was about to say something. Oh, notice that the difference on how the data model. Oh, great. Okay, in Java, typically the relationship flows from the parent to the child, right? So, for instance, if you have a faculty and they have a list of courses that they're going to teach, you might have in the faculty class you might have an array of courses, right? So you can navigate from the faculty, you can navigate down to the courses. Right? And typically, you wouldn't have the other way around, where the course references back to the faculty. Notice that in a relational database is backwards, right? It is the courses that would point back to the parent, okay? And you can navigate from you can navigate either way. You can navigate from the course to the faculty or the faculty to the course, but it is the children who have references to their parent. Right? As opposed to in Java, you have the parents having references to their children. See that? So this disconnect is what oftentimes is also referred to as the impedance problem, the object relational mapping impedance problem. Right? So how do you map these two worlds where it's so different, right, that you treat them? And we'll spend some time talking about that. All right, that's all I have for you.